Welcome. So we know that if we have an LTI system with impulse response ht, and if we apply the input xt under relaxed condition, then the output will be yt equal to the convolution of h and x. Now if you take the Laplace transform of both the sides in this equation, you will get capital Ys equal to Hs multiplied with capital Xs, where capital Hs is the Laplace transform of the impulse response, which we call the transfer function of the system. Knowing the transfer function is same as knowing everything about the system. Transfer function is a property of the system. Now suppose we have a system whose input and output are related via a linear ODE with constant coefficients like this, dny dtn plus bn minus 1 constant multiplied with dn minus 1 y dtn minus 1 plus all other derivatives up to b1 dy dt plus b0 y. This is equal to input x. So this is the standard form of linear ODE relating the output y and input x of many LTI systems. We have studied this before. Let us now make this equation a bit more general by writing the right side instead of the input alone. We will write the input plus the derivative of input dx dt with coefficients say a0, a1, then plus a2 second derivative plus maybe up to mth derivative of the input. This is a bit more generalization of the linear ODE we have studied earlier. Now you can easily show that this equation also represents an LTI system. Okay, now we want to find the transfer function of this system. Now you can do it in different ways. First of all, you know that transfer function is the Laplace transform of the impulse response. So you may first find the impulse response. For that you have to set the input x to be delta function delta t under relaxed condition, and then you have to calculate the output, that is by definition ht, and then you can take Laplace transform. That is one way, but a simpler way to do this is as follows. We know that when the input is delta t under relaxed conditions, then the output will be, by definition, ht, the impulse response. Therefore, if I replace y with ht here in this equation, and if I replace x with delta t, then that should satisfy this equation. Okay, so let me copy this and then I will replace this y with h, here also h, x will be replaced with delta. This you can write as delta dot, delta double dot, and this will be the mth derivative of delta impulse function. Now what we will do, we will take Laplace transform of both the sides. Okay, so Laplace transform of the left side will be equal to the Laplace transform of this right side. Now Laplace transform of this first term, nth derivative of h, will be equal to s to the power n capital Hs. Then this next term will be bn minus 1 s to the power n minus 1 Hs plus dot dot dot. Here we will get b1 constant, then this is the first derivative of h, so that will be s multiplied with capital Hs, and here we will get b0 capital Hs, and the right side will be a0 constant. Laplace transform of delta is 1 plus a1 constant. Laplace transform of delta dot will be s times Laplace transform of delta, which is 1, plus this will be a2 s square multiplied with 1 and so on, plus dot dot dot. Here we will get am s to the power n. Now from this you can easily write capital Hs is equal to this right side. Let me write from the right side, s to the power m am plus am minus 1 s to the power m minus 1 plus dot 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 plus a1 s plus a0 whole divided by s to the power n plus b n minus 1 s to the power n minus 1 plus dot 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 b1 s plus b0, and this is the transfer function of this system. So you see that it is quite easy to get transfer function directly without calculating the impulse response first when the system is given by a differential equation like this. And now if you want, you can calculate impulse response ht by taking Laplace inverse of capital Hs. And also, if you have any arbitrary input given, you can now calculate the Laplace transform of output from this equation Hs xs, and then you can take Laplace inverse to get the output. Okay, so sometimes it is easier to get transfer function directly without calculating impulse response first. Now, transfer function is also very useful to determine the bibostability of a system. Okay, and recall that a system is bibostable if and only if the impulse response ht is absolutely integrable. So this is finite if the system is stable. And we also have seen that transfer function is Laplace transform of impulse response. Therefore, you can expect that there is some relation between the transfer function and bibostability of a system. Systems particularly which are represented by differential equations of this form. Okay, so we have seen that Hs is given by this, the ratio of two polynomials of S, where the original system is described by this differential equation. Then this is the transfer function, and from this we want to predict the stability of the system. The idea is quite simple. And okay, we will assume this m to be less than n. The degree of the numerator polynomial is less than the degree of the denominator polynomial. Okay, and also note that this n is called the order of the system. Because this n is actually the order of this differential equation. Okay, so this m is less than n. Okay, then Hs you can write in this way. So let me factorize the denominator polynomial in the following way. Suppose it is S minus something P1, S minus P2, dot dot dot, S minus Pn. So we have a polynomial which you can always factorize in this way. for some values of p1, p2, pn, etc. Since the degree of this polynomial is n, you will get n factors like this, and this values p1, p2, pn, p1, p2, pn, these are the roots of the equation that Sn plus Bn minus 1, Sn minus 1 plus dot 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 B1 is plus B0 equal to 0. This is the denominator polynomial which is here. If you set this equal to 0 and then find the roots of this equation, that means the values of S for which this equation is satisfied, those values are P1, P2, Pn. Since this is an nth order polynomial, you will get n different roots. Different, or they may be also repeated. Some of the roots can be repeated. Okay, so you can always write this transfer function in this way, and then if okay, this roots p1, p2, pn, they are called poles. p1, p2, pn are called poles. I don't know why, but they are called the poles of the system. And these poles are complex numbers in general. These are complex numbers in general. And then the rule is, if the real part of pk, any pole p1 or 2 or 3 or etc., if real part of pk is less than 0, that means negative for all k, that means for all poles p1, p2, pn, if all these numbers have their real parts negative, then this system is stable. Otherwise, not stable, unstable in Bibo sense. This is as simple as that. Okay. Now, what is the justification of this rule? Okay. So for that, let me start from this equation. And then I can write here small ht impulse response is equal to Laplace inverse of this thing. Now, how do we calculate Laplace inverse? Remember, we use partial fraction. So we will express this ratio of two polynomials inside the bracket as in a partial fraction. So in this way, something like something divided by s minus p1 plus something, call it a1, a2 divided by s minus P2 plus say AK divided by S minus PK. If any root is repeated, suppose PK comes 2 times, same value of P comes 2 times or 3 times, or in general say NK times, so then for that we will get a term like this, AK is to the power nk minus 1 plus dot dot dot, then finally we will get something like say B S plus C. So here this numerator is a polynomial with degree nk minus 1, okay, 1 degree less than this nk, plus so on. Finally you may get an S minus Pn. Okay, now it is possible to write this ratio of 2 polynomials using this partial fraction, because we have assumed the degree of the numerator to be less than the degree of the denominator. Otherwise you have to first divide the numerator with the denominator and then write partial fraction. Okay, so for us we have m, the numerator degree is less than the denominator degree n. Okay, then if you calculate Laplace inverse, what will you get? This first term will give you something a1 multiplied with e to the power p1t ut, then the next term will give you a2 e to the power p2t ut, and so on. Here you will get some signal multiplied with e to the power pkt ut, and then e to the power pn t ut. Now consider any signal e to the power say p kt. If pk is a real positive number, then that signal will be increasing like this exponentially with time. Okay, this is for real part of pk being greater than 0. If it also has an imaginary part, then you know we cannot draw in this 2D plane. We need a 3-dimensional plane with real and imaginary parts separately. Then that signal will possibly look like this. But if the real part is positive, then the envelope of that signal will again increase with time exponentially. However, if the real part is negative, then the signal will decrease exponentially. It may also oscillate depending on the imaginary part, but the envelope will certainly decrease with time exponentially. So it is clear that among these terms, those which have negative real parts, they will die down soon, and those which have positive real part, they will blow up with time. And this is our impulse response. Now if you want to calculate, check whether this impulse response is absolutely integrable or not, so you have to take a mod of this and integrate this. But you can clearly see that if all these terms are exponentially decaying, then this will be absolutely integrable, because after some time the signal will be vanishingly small, so integration will converge. But if any of these terms is increasing, is blowing up with time, then when you integrate the mod of ht, that will not converge. Okay, so that means if all these terms have negative real part, mod ht is absolutely integrable and the system is Bibo stable. But if any of these terms have positive real part, then mod ht will not be integrable, absolutely integrable. Okay, so the system will be unstable. Okay, so we have seen the power of Laplace transform. Now we will also see power of Fourier transform. There is an interesting connection between Laplace and Fourier transforms. You know, consider any signal ht, then the Laplace transform is given by the integration of ht e to the power minus st dt, t running from minus to plus infinity. And Fourier transform of the same signal is integration of ht e to the power minus j omega t dt, t running from minus infinity to plus infinity. Now if we denote this Laplace transform as capital H of s, which is a function of s, then you see that here in place of s, if I put j omega, then that becomes Fourier transform. So if I write h of j omega by replacing s with j omega, then that is same as the Fourier transform of this signal. That means just make the real part of s 0, sigma equal to 0 in hs. Yeah, of course, this Laplace transform must exist at sigma equal to 0. That means this Fourier transform must exist for the signal ht. Then only this is true. For example, if we are considering a system which is described by a linear ODE with constant coefficient like this, for which the transfer function will look like this or like this, okay, and if these poles, that is the roots of this denominator polynomial are such that their real parts are negative, then we know the impulse response will be of this form, and since these real parts are negative, they will all decay down to 0 with time, and therefore such an impulse response will be square integrable, and for that Fourier transform can exist. And then this is true that if you replace S in the Laplace transform with j omega, you will get Fourier transform. So now onwards I will use capital letters with arguments S to denote the Laplace transform of a signal, and capital letters with arguments j omega to denote the Fourier transform of the same signal. So if we feed input xt to a relaxed LTI system with impulse response ht, then the output yt is given by the convolution of h and x, that is integration of h tau x t minus tau d tau, tau running from minus to plus infinity. Now if I choose my input to be of the form e to the power j omega naught t for any value of omega naught, then the output will be integration h tau x is e to the power j omega naught t minus tau d tau, tau from minus to plus infinity. Then this is equal to integration of h tau e to the power j omega naught minus tau, and e to the power j omega naught t I will write outside because this does not depend on tau. Okay, then this is nothing but e to the power j omega naught t multiplied with this integration, which is nothing but the Fourier transform of h tau. So this is Fourier transform of h t evaluated at the point omega equal to omega naught. Okay, and using our new notation I can write this as e to the power j omega naught multiplied with capital H j omega. This is the Fourier transform of impulse response, and this is evaluated at omega equal to omega naught. So if we feed e to the power j omega naught t as the input to this system, we get the output which is exactly similar to the input, except that it is multiplied with an overall constant, which is nothing but the Fourier transform of impulse response evaluated at omega equal to omega naught. Okay, and you can choose any value of omega naught for your input, and this rule will remain unaltered. Okay, so you may in general write this as omega because this is true for all values of omega you like, and so the output is input multiplied with a overall constant. That means this is an eigenfunction of this system. In fact, this is an eigenfunction of any LTI system. Okay, so now we can apply our divide and conquer policy. Suppose we have an input xt, the Fourier transform of xt is say capital X omega, or using our new notation capital X of j omega, that you can get by replacing s in the Laplace transform of x with j omega. Previously we were using the notation x omega, but anyway j is just a constant. Okay, so then we can write xt as a sum of exponential signals of the form e to the power j omega t with amplitude x j omega divided by 2 pi d omega summed over all possible values of omega. Okay, then what will be the output? So let me consider one particular component of the input, which is e to the power j omega t with amplitude x j omega by 2 pi d omega. So this is the amplitude of e to the power j omega t. Okay, and then this signal will get multiplied by hj omega. Okay, so let me multiply this with hj omega, and then we have to add all the components, all the component output for all omega running from minus infinity to plus infinity. That will be the total output. Now this is nothing but Fourier inverse of h j omega x j omega, and from this you can easily say that Fourier transform of y is equal to Fourier transform of h small h and Fourier transform and Fourier transform of x. This is also a very important fact. In fact, this you can derive from yt equal to ht convolved with xt. Okay, and if you now take Fourier transform, then Fourier transform of y must be equal to the Fourier transform of this convolution, and we know that Fourier transform of convolution of two signals is same as the product of the individual Fourier transforms. So this rule you can derive in one line. I have derived it in this way because I wanted to stress upon the policy of divide and conquer, because this policy will now allow us to construct an input-output table like this, where we have different omega values in the first column, starting from minus infinity, then 0, then plus infinity. For each of these omega values, we can calculate h j omega at those values, and then for any input of the form e to the power j omega t, the corresponding output will be input multiplied by this constant, these constants. So this table, these two first columns essentially contains all the information required about a system. If I have these two columns at my disposal, then given any input, I can break it into a sum of exponential inputs like this, and then for each such component, the output will be the same input component multiplied by these constants, and then I can add all the component outputs. So these two columns essentially tells everything about a system, and this is called frequency response. Basically, it tells me how the output or response will be for different input frequencies. Okay? In fact, it is enough to know this function capital H of j omega. If I know this function, then I know what will be the output for different input frequencies, for different exponential inputs with different frequencies. Okay, let me take an example. Suppose the input is xt equal to a sine omega naught t for some values of a and omega naught. What will be the output? Firstly, remember that sine omega naught t is not an eigenfunction of LTI systems. So the output will not be of the form a sine omega naught t multiplied with some some constant. It is not going to be of this form. However, what I can do, I can write xt as a sine omega naught t, which is equal to e to the power j omega naught t minus e to the power minus j omega naught t divided by 2j, and this a amplitude. Okay, then let me call this as x1, this as x2. Then what will be the output y1 corresponding to the input x1? That will be this input a to the power j omega naught t divided by 2j, this input multiplied with a constant, And what is that constant? That is Fourier transform of impulse response evaluated at omega equal to omega naught. In the same way, the output y2t for x2 input, that will be a e to the power minus j omega naught t by 2j with this minus sign, then multiplied with a constant which is h j omega evaluated at omega equal to minus omega naught. And then the final output yt will be the sum of these two outputs, y1 plus y2t. So if I know this function h j omega as a function of omega for all values of omega, I know everything about the system. Okay? And basically this h j omega acts as the multiplicative factor for different input frequencies, or you can call this as the amplification factor or gain factor for different inputs with different frequencies. However, notice that this gain factor in general is a complex number. Okay, so this has both real and imaginary part, or magnitude and angle. So this input signal is multiplied by this complex number. Therefore, both the magnitude and the phase of the input signal may get changed. For example, suppose h j omega at omega naught, so h j omega naught, this is a complex number with magnitude m and angle theta, which you may also write as m e to the power j theta. Okay, then y1 will be equal to a by 2j e to the power j omega naught t, this, then multiplied with m, right, and then multiplied with e to the power j theta. Now these two exponential terms you can write together as like this, j omega naught t plus theta. So both the amplitude is changed, amplitude is multiplied with m, as well as the phase angle of the signal is also changed. To give you a feeling, let me again draw a three-dimensional complex plane. This is time axis, this is the imaginary component of a signal, this is real component. Then suppose this input a to the power j omega naught t by 2j, that rotates like this, starting from some point here. Okay, this is the input, and then when you multiply this with this m e to the power j theta, then its magnitude will be larger, so it will be possibly like this, larger or smaller depending on the value of m. Also, this angle theta will change the starting point of this signal. The input signal was starting from here, maybe the output signal will start from this point here, and this angle will be angle theta. Okay. In the same way, y2, the other component, that will be this input e to the power minus j omega naught t divided by 2j multiplied with this constant. Now, this constant, which is h minus j omega naught, that will be equal to m angle minus theta, because you remember the property of Fourier transform. This Fourier transform at minus omega naught is complex conjugate of Fourier transform at omega naught. So this is complex conjugate of this. So it is equal to m e to the power minus j theta. Now when you multiply this number here, you will get m and this theta e to the power minus j theta. If you write, these two exponentials can be written together as this plus theta. Okay, then you may simplify this y. This is equal to these two terms together. So I will take am common. Then we have e to the power j omega naught t plus theta. Here minus e to the power minus j omega naught t plus theta, and then divided by this 2j. So that will be equal to am constant, and this is nothing but sine omega naught t plus theta. Okay, now in the same way I will give you a homework to show that when the input is say xt equal to a cosine omega naught t, then output will be yt equal to a cosine omega naught t plus theta multiplied with m, where h j omega naught is equal to m angle theta. That means m is the magnitude of h j omega naught and theta is the angle of h j omega naught. Let me write that also. M is the magnitude of h j omega naught Fourier transform of impulse response at the frequency omega naught, and theta is the angle of h j omega naught. Okay, prove this, that is your homework. So this table summarizes the behavior or output of a system for all possible inputs, and this single function hj omega encodes this entire table. So if you know this function hj omega, you can calculate the output for different inputs, any input. So it will be nice to represent this function graphically like this. We will represent with this horizontal axis different frequency values omega, and we want to draw or plot hj omega as a function of omega. However, this is a complex number in general, so we cannot plot this in one graph. So let me take two graphs like this, and in one graph I will plot the magnitude of hj omega, that is the magnitude of Fourier transform of impulse response, and in another graph I will plot the angle of hj omega. Now this may look something like this. However, it must be symmetric, it must be a odd even function, because this is Fourier transform of some signal. So this is even in nature, and this may look maybe like this, and this must be a odd function, because again this is coming from the Fourier transform of a signal. We call this as the magnitude response, and this as the frequency as the phase response or phase angle response. Together these two are called frequency response. If you have these two graphs at your disposal, then you know the value of hj omega, Fourier transform of impulse response, for all possible frequencies, and you can calculate output for different possible inputs. So this frequency response contains all the information required about an LTI system. Now let us ask this question: how can we determine the frequency response graphs of an unknown system experimentally? Suppose we have a system, a black box with an input and output, but we do not know the mathematical relation between the input and output. Can we then find the frequency response in some way experimentally? Remember, earlier we talked about impulse response ht, and impulse response also contains all the information about a system, LTI system, and we can determine this experimentally. You may think of giving a delta signal as the input and measure the output. That output signal will be same as ht by definition. However, ideally we cannot produce delta t impulse signal. Therefore, alternatively, we give an idea that you give ut as the input and then measure the output yt and then calculate time derivative of this output. That will be same as ht. We studied this before. In the same way, is it possible to find h j omega experimentally? You can think of an experiment that you give input e to the power j omega naught t, and then we know the output will be of the form e to the power j omega naught t multiplied with something, because this is an eigenfunction. And what is this something? This something is nothing but h j omega naught. That is the value of Fourier transform of impulse response at the frequency omega naught. Then you may vary this frequency omega naught. Suppose you have a control knob with which you can vary this frequency, increase or decrease it. Then you give different frequencies, call that omega in general, and you will get different outputs. Okay, now if I write the magnitude of h j omega as m, that will be a function of omega, of course, since h j omega is a function of omega, and the angle of h j omega as theta omega, then this will be equal to m omega e to the power j omega t plus theta omega. Now you can vary this input frequency omega starting from minus infinity to plus infinity and record the output, measure these two factors m omega and theta omega, and then plot m omega and theta omega as a function of omega, like this. M omega as a function of omega and theta omega as a function of omega. That way you can get the frequency response. Okay, but you know, this is not possible in laboratory. It is only possible in our imagination, in our understanding. Because how will you produce a complex valued signal in laboratory? I mean, we can only produce real valued signals, not complex valued signals. So alternatively, we can do the following. We will give input of the form sine omega naught t or cosine omega naught t if you like, and then we will measure the output. But we know for an LTI system, if you give sine omega naught t as the input, then the output will be of this form. Okay, m sine omega naught t plus theta. If you give a sine omega naught t as the input, this will also be am sine omega, or let me write this way, m into a sine omega naught t theta. where we know theoretically m is equal to the magnitude of h j omega naught. Okay, we wrote that here, and theta is the angle, and theta is the angle of h j omega naught. Now you can change omega naught, you can give different frequencies and record what is the output that you observe. Since you know the amplitude of the input, you can measure the amplitude of the output, and then if you divide this amplitude with the amplitude of input, you will get m. Okay, so let me draw. Suppose this is your input sine omega naught t, then the output will be magnified by a factor of m and advanced by the phase theta. So that will be something like this. So it is magnified by a factor of m. So this height will be ma if this height is a, and it is also advanced in time by an angle of theta. Okay, this starts at time 0, this starts earlier, and you can measure this angle theta and the amplification factor or gain factor m experimentally. That is possible. And also this magnitude, it will depend on the frequency of the input. So let me write m omega naught, function of omega naught, and this also function of omega naught. So here also I should write function of omega naught, and this also function of omega naught. And you can vary your omega naught, you can vary omega naught, and then you can record the amplification, magnification and phase shift for different values of omega naught, and then you can plot it like this as a function of omega. Okay, great. Let me demonstrate frequency response with some experiments. Okay, consider this pendulum. Some weight, paper weight is tied with a rubber band, and I am holding it here, and I can move my hand up or down. Okay, and the position of my fingertip from some reference level up or down, that is considered as the input to this system. I can move it up or down, up or down, and then the position of this weight also changes, it goes up or down, and this position from some reference level is considered as the output. Now I will give sinusoidal input. That means I will move my finger up and down sinusoidally like this, up, down, up, down. It's not perfect sinusoid, but I mean that's the best what I can do here. Okay, and then so that is my input. Then this pendulum also moves up, down, sinusoidally. Now you have to watch the amplitude of the input. That means how much I am moving my finger, like this is the amplitude from here to here, here to here, and the amplitude of the output or the position of this weight, you also have to notice how much this is moving. For example, now the amplitude is from here to here, here to here, and then you have to calculate the ratio of output amplitude divided by input amplitude. That will be the magnitude m, or mod h j omega for some frequency omega. And I can also change the frequency of input, like now the frequency is very slow and now the frequency is very fast. Okay, so I will change the input frequency, and you have to find this ratio of output amplitude and input amplitude at different frequencies, and then we will plot that as a function of omega. Okay, m versus omega. So let me do this experiment. First, at very low frequency, let me do the experiment. Up, down, up, down. So you see the amplitude of this weight is almost same as the amplitude of my finger. As much I am moving my finger, the weight is also moving by the same amount. So at very low frequency, this ratio will be 1. So if this point is 1, it will be something like this at a very low frequency. Then let me increase the frequency. Now you see that my finger is moving very little, but the weight is moving quite large. So at a higher frequency, this gain will be quite high. So it goes up. I don't know the exact pattern, I mean straight line or whatever. Okay, but it goes up. Then let's see what happens at a higher frequency or very high frequency. You see my hand is moving, but the blob is not moving that much. Let me do it with my right hand. You see I'm moving my hand quite fast, but the blob is not moving. You should do this experiment yourself to convince yourselves. So at very high frequency, this gain will again come down to almost zero. In fact, my hand is moving, but the blob is not moving. Okay, so this is what is the magnitude response. Now let us try to find out the phase response. Now what is phase? Theta. What is theta? Angle of h j omega. How do we measure this? For that, you have to observe more keenly whether there is any lag or advancement between the movement of my finger and this blob. At very low frequency, you see they are moving together. When my hand goes up, this weight goes up. When my hand goes down, the weight goes down. Okay, so if my hand is moving as a function of time in this way, then the weight is also moving in the same way. There is no phase difference between the two. So at low frequency, the phase difference between output and input is 0 at very low frequency. Okay, let me draw it here. Then let's see what happens at a larger frequency. You possibly cannot see this, realize this in the video, but when you do this experiment yourself, you will realize that there is a gap, phase gap between my hand movement and the square movement. You will realize when you do this yourself that actually when I am moving it up, it is going down, and when I am moving it down, it is going up when at a particular frequency. I mean, I don't know whether it is visible in this video, but if you do it yourself, you will feel the force in your hand, and you will realize that when I am moving it up, the weight is going down, and vice versa. So there is a gap, in fact almost 180-degree gap at some frequency. So that means at a higher frequency, when I am moving my hand in this way, the weight is actually moving in this way, almost in this way. So there is 180-degree phase difference between the input and output. So at a higher frequency, this goes down to 180 degree. This point is minus 180 degree. Okay, and you can do this experiment for different intermediate frequencies and try to realize what is the phase gap between input and output. Okay, another very simple experiment that you can do right now together with me, if you just have a pen with you. So do this. Hold the pen lightly. Okay, hold the pen lightly between two fingers, and then move your hand up and down. Okay, and then the motion of your finger is the input. So that goes up and down, that is the input signal, and the other end of the pen, that is this end, will also go up and down, and that motion is our output signal. Okay, and you can change the frequency of the input. To do this experiment, remember to hold this pen very lightly. Do not grip it tight. I mean, as lightly as you can, very lightly. Okay, and then you do this experiment by giving different input frequencies like low frequency and then high frequency or higher frequencies, and you have to record the magnitude or amplitude of output divided by amplitude of input as a function of omega, and whether there is a phase gap between the input and output as a function of omega. So observe carefully and also do it yourself with a pen. At very low frequency, input and output moves together and their amplitudes are same. So at low frequency, this ratio is 1 and phase difference between input output is 0. Now at higher frequency, possibly you can see that there is a phase gap between the input and output, and when I increase the frequency, there is almost 180-degree gap between the input and output. When I am raising my hand, the tip of the pen is going down and vice versa. So at high frequency also you saw that the gain increased. Okay, the gain increased first. So here the input amplitude is less than the output amplitude. So this M goes up and we get some phase lag between input and output. Okay, by the way, this system that I am demonstrating, it may not be a LTI system at all, but that is not crucial at this moment. This is to demonstrate you the idea of magnitude and phase response. Okay, that's it for today. See you tomorrow. Bye.